would like to do is reclaim mathematics as a fundamentally beautiful and creative art form. And just talking to some people in the past day, there's a lot of math phobics, which is common. People have learned to hate math. And when I say math, what you're thinking is probably not what math is. What you're thinking about is probably that thing you learned in school that they tried to make you do, and there were numbers and equations. And that's not what math means to me. So I want to show you what I do with math, how I have fun, and kind of show you through my eyes, through a series of projects. So I have this YouTube channel. This is how most people know me, because math should be informal. It should be something you explore. It should be fun. It should be doodling in your notebook when you're bored in class, which is kind of what I do in my videos, but those kind of speak for themselves, so I'm not going to talk about that today. I come from a geometry background, so this shape is a dodecahedron. The actual thing is a melon. It was quite delicious. But when you make a mathematical thing for real, you are learning about something about it. When you have an abstract concept, there's so many different ways of thinking of things, and when you build it, you really learn something, some aspect of that thing. So when I make a dodecahedron by cutting up a melon, the process, the thought is, okay, we're starting with this kind of spherical melon, and now with just 12 straight planar cuts of a knife, you can make this. So in order to figure out how to make those cuts, there was some details involved. It wasn't exactly just 12 chop, 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 however many that was. But you have to think mathematically, how am I going to make this? And you're thinking from the perspective of building it from the planes of the different faces. And you just make those 12 planar chops, and this is the shape you get, and that's kind of amazing. But you can think of the same shape in a different way. Oh, wait, I kind of followed up this project with some other shapes. Like a cube, you just know, all right, you make a slice that's parallel to that, then you can turn 90 degrees, make 2 more slices parallel to each other, turn 90 degrees the other way, and bam. And now you were thinking about planes and perpendicular planes, and you end up with a cube. But maybe you weren't thinking about squares, and putting together squares is another way to think about the cube. There's tons of ways to understand mathematical objects. Another way to think of a dodecahedron is, okay, you get 12 pentagons, in this case made of glass, and you just stick them together 3 at each corner. And if you just stick together pentagons 3 at each corner, you can do that with paper or anything, you get a dodecahedron. And then you didn't have to think about slicing in planes at all, but you learned something else. Or you can think about the edges. So in this case, I made a dodecahedron out of balloons. And the thought was, okay, now I'm going to just be making the edges of it. It's going to be hollow. How do I have to think in order to create that? Okay, well, now what a dodecahedron is something that has all of these kind of lines that are the same length. And they're coming together 3 at each corner. And you're putting them together kind of in a cycle of 5. And then there were other considerations. All right, out of balloons, well, I wanted to make it out of the least number of balloons possible. So that ended up being a really fun mathematical and computational geometry question that I got a couple papers published out of with some of my co-authors of ideal design of polyhedra out of balloons. And that led to other stuff out of balloons. This is like this tangle of balloons with this symmetry comes from a mathematical tangle, and just exploring the space of possible ways these are squares all linked up to each other with kind of the symmetry of a cube. You can imagine that if each of these squares was the face of a cube, and then you just kind of push them in and twist a little, and they all link up. And this is another tangle, and a hyperboloid in this case. So I got into balloons. And the theoretical question was, all right, so I want to make this icosahedron. So here's another shape, except it's related to the dodecahedron, which was the first one with the pentagons, but now it's okay, we got triangles and we're putting them together 5 to a corner. Or maybe we're taking a sphere, but then we're cutting planes, 20 of them to make these 20 triangles. Or maybe we're thinking about the edges and having the edges meet 5 at each place. Or maybe we're thinking about symmetry and we're starting from a pencil and paper and thinking about group theory. There's tons of ways to arrive at this shape. When you make it, you feel these different ways. So the question was, how do I make this out of the least number of balloons possible? You can't make it out of just one really long blue balloon, because if you start going around, you realize you get stuck, because each corner of this has an odd number of balloons coming in, and each balloon only has 2 ends, so there's not enough balloon ends, right? It can get very theoretical, and this was the answer, is out of 6 balloons that can be arranged very symmetrically. So that's just an example of how kind of the artistic wanting to make a shape can lead to some interesting research, some cool results. Here's another, this shape could be made out of just one balloon. So when we were theorizing about, oh, yeah, if it has an Eulerian cycle, then you can make it out of just one balloon. And then that was math first, and then actually try and make it. The words I'm saying that you might not understand are not as important as just saying, we were thinking about math, and then it was cool, so we made a thing. Right? That's kind of how I work. Okay, and then balloons were great, so I did some workshops with balloons and making stuff. All right, here's some bottles. Actually, I think I come back to bottles later, but that's the icosahedron made out of bottles. Smarties are a delicious building material, and a good excuse to buy a giant bag of Smarties. Lollipops of this might look kind of messy from the outside, but from the inside, all those lollipop sticks are arranged in a very mathematical way. You can see this kind of pentagon with the triangles around it. Okay, so those were Polyhedra. Fractals are also really awesome. This candy corn, Sierpinski's triangle, was just made out of a simple process of you start with one piece of candy corn, and then, all right, wait, I'm going to kind of draw this out. I have a pen. Okay, so, oh wait. That's wrong. I need to turn on this. Okay, so I start with a piece of candy corn. And the only rule I'm following here is here we have no candy corn. So if you have these 2 places where there's exactly 1 candy corn next to 0 candy corn, under it we put a candy corn, so that happens here too. Where if there's no candy corns next to each other, you don't put a candy corn under it. And if there's 2 candy corns next to each other like here, then under it you put no candy corn. That's the only rule, right? If there's exactly 1 candy corn, under it you put exactly 1 candy corn. So simple, but that's a mathematical rule that ends up making this triangle design, and you can keep going infinitely, and that's one way to think about this fractal. But there's other ways to think about this fractal. There's actually a ton of, you could do an hour-long talk about just different ways that you get this form that are completely different, and it would blow your mind, but I'm not going to do that. Okay, so the hyperbolic plane, when we were talking about putting triangles together, you can put so many triangles together at a corner and you get some sort of shape. If you put 6 triangles together at a corner, you get something flat. Like you can also tile hexagons together, 3 to each corner, and you get flat honeycomb pattern. Or if you have squares, you put 4 around each corner, you get a flat floor tiling. If you put too many things around each corner, in this case 7 triangles, it's kind of this hyperbolic tiling, and you have hyperbolic geometry, and it's this kind of fundamentally different way of thinking about space. But I wanted to make that, not just look at my diagram where you have to squish all this stuff, then it gets smaller and smaller at the edges, and everything's all wonky to try and fit this flat to show it one way, and you can kind of see the infiniteness, how it doesn't fit. Or you can make it out of balloons, and that's another way to think about it with those edges. And that led to other questions about infinite tilings and how to arrange these balloons and stuff, but not going to go into that. And here's another example of a hyperbolic tiling. First the tiling, and then its version out of balloons. And here's another. So I like the balloons. They have this problem. This happens. So then I thought, okay, let's have something that's kind of like a balloon, but it doesn't melt. And the first thing I thought to get about when stringing together these balloons was beads and beadwork. So here's a little hyperbolic plane made out of these beads, and it's just following the simple rule that right, instead of 6 beads around each loop, you get a honeycomb flat pattern. I put 7 beads around each, and then you end up getting this curvy thing, and these just awesome mathematical forms. Okay, so I like that I'm kind of coming back to this whole plastic idea, because when I lived in a town that had just not great water at all, and I found myself buying all of these water bottles, and they were just kind of piling up, these empty water bottles. And eventually I realized, what am I going to do with all of these bottles? This is terrible. And I was also thinking, okay, this beadwork is kind of cool. I wish I could make giant beads and make something really big out of beadwork. And so I put one and one together and made a double water bottle bead. And so I made a whole bunch of those. And started stringing them together. So here are these polyhedra made from beadwork. And then there's these other considerations where, because unlike beads, which you can kind of string tight together, these water bottles, well, if you tried to make a cube, it would just kind of like flop and collapse because the squares, a square is not rigid, but so I had to think about shapes made out of only triangles. So these 3 are some great triangle shapes. And of course, I had to make a hyperbolic plane with 7 triangles around, so I ended up with this big kind of reconfigurable bottle hyperbolic plane that you could make into all these shapes. Yeah, like that. Okay, and then now that I'm thinking about these shapes and kind of visualizing what before, when you learn about the hyperbolic plane, they don't usually teach you that it can exist. They just draw these diagrams, and you learn the geometry of it, and it can be very pencil and paper. Pencil and paper is great, but pencil and paper without enough pictures is the problem. It's possible, and it's also one of the great strengths of mathematics that you don't have to understand what something looks like to work with it and get results. You don't have to wrap your head around the entire concept for mathematics to work, which makes it a really strong tool. But it's also missing something if you do that too much and kind of forget about the beauty that's there. So after working with making these hyperbolic planes and getting a sense of how they feel, how they move, what they really are, not just as numbers and proofs and lemmas and lines and stuff, but what they are, you start seeing them everywhere. You see them in plants and in life, and in the way that a dried apple slice curves. All of a sudden, I'd never realized before, even being involved in mathematics for a long time, that a dried apple slice has this beautiful curve, which somehow it's hyperbolic. And now that leads to whole new questions of, okay, how come when an apple slice dries, it gets all curvy? Like, we take it for granted that when stuff dries, it gets all like curly, but something's going on there. There's some transformation that is taking something that's flat and changing the geometry of it. And that's a really interesting question. Why should something get all crinkly when it dries? I mean, all right, so there's less water and there's more everything else, but why doesn't that just scale everything down? And some things, like if you look at a dried banana slice, it does just kind of get smaller. It doesn't get crinkly. So that some stuff does that and some doesn't is like something is going on with the geometry. There's mathematics there. And yeah, here's some more pictures, some experiments trying maybe if there was no skin, maybe if you sliced it a different way, but how do you get to the heart of this problem? And then the real test of if you kind of understand the form of something is if you can draw it without making it, I mean, because the stuff I showed you before, you're putting together bottles in a certain way, you get this. You put together too many of a polygon, like stuff just works in mathematics. You put together things in a certain way and you get the result, right? So what if just thinking abstractly, trying to draw, can I draw something that is and looks hyperbolic? So these are just some experiments in trying to wrap hyperbolic planes around itself. And they're not perfectly mathematically hyperbolic. It's an artistic hyperbolicness where just everything should have the right curve. And that was kind of a test of my visualization skills. So I made this drawing, and I thought, oh yeah, this kind of seems like a hyperbolic ghost. I can see like the dress of this ghostly figure, and I wanted to make one of those. So that brings us back to plastic. Another one of my problems was I had this closet full of plastic grocery shopping bags. And they just build up. It's like at first you think you save them and you're going to use them as your garbage bags and they're all going to go away somehow and like it'll balance out. And you don't. You just end up with this pile up of plastic bags. And I've since switched to canvas, reusable shopping bags. But all right, what better material for a light and flowy thing I want to make than this light and flowy plastic? So whereas if I made hexagons, I could kind of put them together flat, and you get something flat. But instead, this has 7 sides. It's a heptagon. And if I put those together, it should get something hyperbolic that's curvy and flowy. So I did. I cut out just a whole bunch of these, and I ironed them together, which was actually kind of tough. I don't particularly recommend it. But I did it anyway, and ended up with, oh, this is kind of a dark picture you can't see. All right, well, there was this kind of flowy thing going on. I need a better picture of that. You have to imagine it. It's a visualization exercise. And then this was a painting starting to think about how maybe a hyperbolic piece of paper might fold. It just has different rules than a flat piece of paper. If you have a flat piece of paper, you can't fold it like one way and then turn it 90 degrees and fold it the other way, and then you can't fold both those lines at once. It's like one or the other. Hyperbolic plane, that's not true. It has different rules. So thinking about that, okay, right, I'm a musician. So I like to write music, and I like math, and eventually I put the two together because writing music can be like a puzzle sometimes. Any artist, having a limitation, some limitation to your medium or your subject is really a great way to inspire just doing stuff you might not have thought of otherwise. And it's a challenge, and that makes it like a fun puzzle. So I'm just going to show just a few examples. This is a self-referential string quartet. Right, so binary numbers are cool. There's zeros and ones. And music, rhythm is essentially binary. There's play and there's rest. That's how you define rhythms, is when you play and when you rest. There's not worrying about notes. So it's binary. So I can put 1 and 1 together and say, all right, 0 means rest, 1 means play. Now, any number I can translate into a rhythm. Rest, play, play, rest. 0, 1, 1, 0. Now I can add a melody to that just using my own artistic license, because I think it's great to have some restrictions and then some freedom. And kind of say, working within this rhythm, what can I do? And then I get to have fun. So ASCII code is the code where each of these set of 8 numbers represents a letter. So, and then here, right, 0 is rest, 1 is play. It goes on like that. So we've got letters. There's a secret code here. So I'm going to just play this and show what letters it is. So each instrument plays its own name. And you can imagine, that didn't, if I didn't tell you, yeah, I did this thing with binary numbers and rhythm, like you wouldn't realize there was a secret message in there. But it's completely decodable. If I play that for someone who then wrote it down and I told them, yeah, that's binary numbers, it's ASCII code, they could completely decode it all. The information is there. So now you can write all sorts of secret messages in music. Here's just another example using the Fibonacci sequence, which we had a good conversation about how it's in pine cones last night. But here it is in music. So the idea for the Fibonacci sequence, well, the big idea is that you have 2 numbers, you add them together to get a third. Then you add the second and third, and you add them together to get another, and you just keep adding, getting another, adding, getting another. And if you start with 1 and 1, it's 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. You can start with other numbers, which is why pine cones can sometimes start with other numbers, but they're usually Fibonacci. So what about music? We could do this in music. And here I just changed the rule slightly that you can hold your note over a rest. So if you start a note, it's a 1. If you don't start a note, it's a 0. So this is 1, 0. So for example, here we have 1 plus 1 in the flute, and they play at the same time to represent adding them together, and they play 1, 0, which in binary is 2. I'm just going to play. So here's a 1. Right, and so on. So, oh wait, yeah. There's a little secret here too. If C is 1, and then D is 2, and then E is 3, and then E, F, G is 5, you also get some Fibonacci sequence action in the melody. Okay, so that was another. That's just we're kind of playing and having fun with math and music. All right. So here's another project. This is for an exhibit in the Math Midway, which is a traveling exhibit of the Museum of Mathematics. And all right, so they wanted me to make something to play along with the organ function grinder where people are choosing a number to put in and some stuff to do to it, like add 3, halve the number, and then invert them, or make it 1 over x. Just these different processes. You could double the number, you could take the square of the number. So you can string along a bunch of these things to do to the number. And what might that mean musically? What might play along with this? So I just kind of made, I said, all right, we're going to take 9. Let's say 9 is this melody that I wrote and has some harmony that I wrote. All right, so if this is 9, what might add 3 mean? Maybe we add 3 half steps. So now this note goes up to this note. That might be cool. All right, so now we can add 3 to any melody under this definition of add 3. And all right, how about halving? Well, we could just have the note value. We could say this quarter note becomes an 8th note. And now we can have any melody, or double it by making it twice as long. And inverting is a pretty popular, well-known musical theory thing where you just turn the stuff upside down. Instead of going down here first, we go up here first. You can turn any melody upside down, and that's an inversion. Okay, so now we can do all these things to a melody, and I can think, okay, let's write some starting melodies that I know are going to sound good when we do this stuff to them, and see kind of what happens. So this is 9. Now it's higher. Now it's faster. Now it's upside down. Ta-da! And here's another example. Here's 7. Now it's lower. Now it has harmony, and now it's slower. So that was pretty cool because by just writing a whole bunch of starting melodies and coming up with these algorithms for how to change the melody based on what buttons you press, I effectively wrote like 2,000 pieces in a week, which I think is pretty good. Oop. Yeah, all right, and then I get to think about other things like, all right, what about imaginary numbers? If you take the square root of a negative number, what does that mean musically? Imaginary number, or taking square roots of negative numbers. So musically, here's what I did. So here's our melody for 64. Now it's upside down. Now it's lower. And now so I just had to take the melody, put it up 2 octaves, and change the scale of it. It's all done by this machine computer, and it was kind of like a fun thing because especially kids playing with this exhibit would think about, what would happen if you take the square root of a negative number? And now they're kind of exploring and discovering something cool that happens. And you all should know that dividing by 0 is a great way to break a program. And when you want to kind of kid-proof a museum exhibit, you have to think about, all these kids who are going to come to your machine, and then they want to mess stuff up. So what happens when one of those kids comes up and tries to divide by 0? Here's an example. So we start with 09 again. Square root is 3. Now we're down to 0. Now we divide by 0. Oh. Well, not every exhibit can be a winner. Okay. I'm going to skip all the videos, because that's on the internet. I have other stuff to talk about. There's symmetry. Music, here's the inversion where you just turn it upside down along this line. But you can also make stuff go backwards. That's, we got some good symmetry going on. So freeze patterns are when you kind of have a repeating pattern, basically. And it could just be something that repeats. Or it could have other symmetries, too. Like this, for example, has these mirror lines where it goes down here, and then the music goes up here. It's symmetric along all of these lines. And then it's got these points of rotation where if you spin the music around that point, you get the same exact music. And you can kind of find these patterns in music all the time. When you have repeating things, you have arpeggios going up and down, and there's so much symmetry and beauty there. And composers do this all the time by accident. These patterns are everywhere in music, and you can kind of analyze and categorize. And certain composers prefer certain ones, and you can see this stuff is there, and there's some aesthetic sense that makes us write this stuff without thinking about the symmetry. I mean, sometimes composers do think very hard about symmetry, but often it's just entirely intuitive. And there's 7 different kinds of them, and I wanted to kind of do that on purpose. So, is this playing an example? Is the sound need to go up? No? All right. Well, that's okay. Maybe this will play. All right, here's an example of what's right now isn't what's playing. Kind of going up. So that was just a symmetric little piano thing, but also in parallel. So you just have, all right. Yeah, all right. I want to get back to kind of some physical stuff, because what I want to talk about a little is collaboration and how to kind of empower people to do their own mathematical cool stuff. So I'm going to show some pictures from some workshops I did. Here's a picture where we made, this is Sierpinski's triangle again, made out of pennies with a group of students. And there's a 3D version that we made out of balloons at another workshop. And here's something made out of laundry baskets. Often I work by going to a dollar store, seeing what is kind of cheap and big and cool and could probably be put together. And then in this case, I brought it back and I said to these students, all right, I have these laundry baskets. I think we could probably make a dodecahedron, right? If we have 12 of them and we put them together like the faces of that dodecahedron. That was the first few slides I showed you, was with these 12 pentagons. So each of these laundry baskets it connects to 5 neighbors. So that's like the pentagon. So that's the symmetry, that's the shape. But at first it wasn't working out. I was trying to make it with the baskets facing out. And kind of I can get away with just going places without much of a plan, saying, yeah, let's try building this, because then I can trust the students to come and say, I have an idea. What if we flipped it inside out? So that's what the student did. And then it worked out. We flipped it out and it worked. So kind of going places not with a real plan and trusting people. And here's another laundry basket thing we did. And again, I had this vague idea, all right, we could put together all these green and blue baskets, kind of like the faces of an icosahedron. And it kind of wasn't working out, it was floppy, and then the student said, all right, what if we had more laundry baskets and we put those in the spaces between, and that would give it more structural integrity. So we tried that, and together we came to a solution that worked and made this kind of big, crazy shape that was very imposing to sit and drink hot chocolate under. And this out of plastic swords. We were putting together these plastic swords, and I had some vague idea about one thing, and it wasn't working, and together we figured out how to make it into this final symmetric result, which also made a very nice hat. And this was made of clothes hangers with some people like, all right, how can we put these together to make it work? This was a workshop with whisks. This piece is called Whisk Management. And this is out of umbrellas. I managed to catch some unsuspecting students. So this is a hyperbolic plane by putting together umbrellas a certain way. And we did this, and this just took a lot of kind of, oh, hey, everyone, how do we hang this? How do we make this work? And we ended up, right, I had these vague ideas of hanging it from like one point, but students were like, no, we'll string it from one balcony to another. So it ended up working out. And then a student had this awesome idea. She said, how about we grab some whiteboard markers, and then we can have like this collaborative poetry space, and we can all like draw and write poetry together on this like giant hyperbolic whiteboard. So we did, and that was just like really cool. That added just so much personality to it. And I would have never thought of something like that. And then I'm like out of time, so I'm going to just quickly flip through. This is pictures where really I didn't make any of this stuff. I just provided the materials, and I said, all right, let's try making some mathematical stuff. If you had a bunch of stove liners, just think. So people ended up making Polyhedra, and what if you have a bunch of crayons? Let's just play. Let's bring the play back into mathematics. Let's be creative, because mathematics is creative, and we're missing all these creative people who should be doing great mathematics and aren't, because the mathematics they were taught in school made them think that mathematics was not a creative field. And most recently, I've even gotten rid of all the materials and have been doing workshops with human geometry, trying to figure out how do you make a cube with your fingers. And designing and thinking about how you do this stuff is just like, it involves so much mathematical thinking. And just, yeah, math is cool, collaboration is cool, and the results are pretty awesome too. Thank you.